All right, so kinematics says here is the study of the motion of a particle in a straight line. All right, so that's the key thing. We're just working in a straight line. I guess a few definitions. We tend to work in meters per second, but to convert from meters per second, kilometers an hour to meters per second, we multiply by 5/8. Position, okay, where the particle is at any point in time. Displacement is the change in the position as opposed to the distance, okay. So positive displacement, so displacement is a vector, positive to the right of the final position, negative to the left. 0 means we're at the starting position. Distance, on the other hand, is the length of the path taken, yeah. So you might have a displacement of 0, but you've gone up and gone back, so your journey's been a little bit longer. So clearly there, just very quickly with example 1, the displacement of a body, an object moves 15 meters to the right, so it moves 15 meters to the right, and then comes 6 meters back. So clearly, so we've traveled 16 and then we've moved back, sorry, we've traveled 15 and we've moved back 6. So my displacement is this distance here, which is 9 meters, but obviously the distance I traveled is 21. Yeah, the 15 plus the 6. All right, velocity and speed. Velocity, okay, is my vector. That's the average rate of change of the position with respect to time. The average of anything, remember the average of anything is that sort of gradient form, y2 minus y1. So there's my y2 minus y1, except this time it's my position. What's the change in position over the change in time? The instantaneous anything is my derivative at the point. So that's my dx dt. Speed itself has no direction, so that's the scalar quantity. Okay, it's just the distance travelled over the change in time. All right. My velocity, my average velocity is the change in position. So it's quite possible we've done all this travel, but again, if we end up back at the starting position, well, my average velocity is 0. Okay, because my change in position is 0. Acceleration, again, that's the rate of change of my velocity. So average acceleration, again, y2 minus y1 kind of thing. Instantaneous acceleration, okay, is the derivative at the point. So the change in velocity over time, which is the second derivative of the change in position over time. So just keep that in mind, that's that relationship through. All right, and then there's a few little facts there. I guess just to note, close to the Earth's surface, acceleration is acting on a particle is due to gravity, and we take gravity as acting as 9.8 meters per second squared down. All right, so that's the rate at which, I guess that's our change in velocity, if you like. That's gravity, we take it as negative 9.8. Kinematics, we tend to work with the 9.8. Not so much in mechanics, we just tend to use G. We leave everything in terms of G, all right? And there's just a summary of the relationship between our displacement, velocity, and acceleration, all right, in terms of integrating or differentiating. All right, let's have a look at a couple of examples, all right? So a particle moves in a straight line, so that its position relative to the origin is given by x equals 3t squared. 3t minus t cubed plus 2, where t is greater than or equal to 0. All right, initial position just means t is equal to 0. Position when t is equal to 2 sort of makes sense. We substitute the value in. Initial velocity, we need a velocity rule. So velocity is dx dt. So that's 3 minus 3t squared. At t equal to 2, we just substitute that in. So we get negative 9 meters per second. The speed, okay, is just the magnitude of the velocity. So our velocity with a negative gives us direction. So it suggests we're heading away from the origin. All right. Sorry, heading to the left of the origin, but at a speed of 9 meters per second. When and where is the velocity is 0? Okay, so obviously we solve our velocity rule equal to 0, gives me t equals plus or minus 1. But t is greater than 0, so we don't have to worry about t equal to 1. And at t equal to 1, the position, the where, is 4. Okay, so my velocity is 0 after 1 second, and we're 4 meters 4 meters from the origin. All right, so it's exactly the same equation, you'll notice, okay. I've got some of the questions double up, but some a little bit different. When and where is the position 0? Okay, so we've got to solve our position vector equal to 0. So I've just done a little synthetic division here, and we end up with t plus 1 all squared as our other factor. So we can guess and check to get our t equal to 2, but the other solution at t equal to -1, again, t is greater than 0, so it doesn't make sense in this particular instance. So it's only at t equal to 2. We're going to have the particle back to the origin. When the velocity is 0, the position acceleration, so we sort of worked out when the velocity was 0 previously, that was a plus or minus 1, again just a positive 1. Acceleration is given by 6t, so at t equal to 0, I may not have worked out the acceleration there at that point, did I? Acceleration, so acceleration at 1 was equal to 6 meters per second squared. Okay, left that out there. That's a bit better. Keep moving through. So the position, when is the acceleration 0? Obviously 6t equal to 0 implies t is equal to 0. So that particle is 2 meters to the right of the origin, and it's traveling at 3 meters per second, so it's traveling further right. The distance traveled in the first 3 seconds. So once we get to the distance traveled, okay, I think it's a good idea to do a little velocity time graph. Well, in this case, I've done a position time graph. So we can sort of see our particle starts at 0, 2. We know from the previous example it gets to 0.14 before the velocity is 0 and then stops and turns around. At t equal to 2, the particle is back to the origin, and then it continues on. And at t equal to 3, we substitute 3 in here somewhere. At t equal to 3, our particle is -16 meters. Okay, so total distance, well, how far have we journeyed? In the first part of the journey, we traveled from 2 up to 4, so that was 2 meters. And then in the second part of the journey, I traveled from 4 down to -16, which is a total of 20 meters. So we've traveled 22 meters in total. So if you like, our average speed was 22 over 3 for 3 seconds. The average velocity, well, we're -16 meters at the 3 second mark, so it's -16 over 3. Sketch the graph of the displacement time graph, and we've done that there. All right. A couple more examples. So again, we've got a particle moving in a straight line, pass through a fixed point with velocity. The acceleration A of the particle times t is given by, so there's my velocity. Oh, there's my acceleration. Oh, get rid of that one. There's my acceleration there. All right. So find the velocity. So acceleration is dv dt. So if I integrate dv dt, I end up with a rule for v. So v is the antiderivative of 12 minus 6t, which gives me 12t minus 3t squared plus some constant c. At t equal to 0, we had a velocity of 30 meters per second. So that gives me c is equal to 30. So there's my velocity equation. And at t equal to 3, the velocity was 39 meters per second. All right. So the time taken to reach the maximum distance from the origin. So the maximum distance from the origin in the initial direction means how far have we traveled until the velocity comes to a stop, the particle comes to a stop, and then we turn around because we had a cubic here. So velocity dx dt equal to 0. So that's my velocity rule. A little bit of factorising tells me that at t equal to 2 plus root 14, because 2 minus root 14 will be less than 0. That's when we reach our maximum distance. The value of the maximum distance, well, to find that value, we need a rule for the distance. And so we do have dx dt, and the velocity is dx dt. So if I integrate that, I'll get an equation for x. which is there, plus d, but at t equal to 0, everything was 0, so that constant is equal to 0. If I substitute 2 plus root 14 into that equation, courtesy of our calculator, we get 180.766 metres, which is just here on the left. You can see the CAS dump for the key values there. All right, what about if we've got a cricket ball projected vertically upwards from the ground, experiencing a gravitational acceleration of 9.8 metres per second squared? Okay, so it's going up, so gravity acting against us. So my gravity is negative 9.8, so gravity acceleration, okay, dv dt. So again, if I integrate that, I get velocity is negative 9.8 t plus c. Again, put my initial condition in. The velocity, initial velocity of 25 gives me an equation for velocity. At t equal to 2, we put that in, and I end up with 5 point something there. What's that say? 5.4. Okay, meters per second. All right, the height. So to find the height, I need a rule for the height. So I know velocity is dx dt. So again, I integrate, make my way through. Again, plus d, but at t equal to 0, we're starting from the ground, so d is equal to 0. So there's my rule for the height of the particle at any point in time. So if I put t equal to 2 in there, I'll end up with 30.8 meters. The greatest height, well, the greatest height is going to be when the velocity is 0. That's when it's going to stop and start falling down. So the velocity equal to 0 gives me t equal to 2.55. Substitute that into my rule, and I get 31.89 meters. How long does it take to get back to ground level? Well, this means my position. My position is 0. So if I solve x of t equal to 0, I get a nice little factored form. So at t equal to 0, which makes sense, I'm starting there, and at t equal to 25 on 4.9, which is 5.1 seconds, we expect it to come back. It's worth noting, of course, that if it takes 2.55 seconds for the particle to reach its maximum, okay, it's going to take exactly the same amount of time for it to come back down again, because of the symmetry of the whole thing. So we could have approached it in that way as well. All right, off you go.